What about the
Let me guess. Gonna get
yeah.
a glass of water. I'll be right
Oh, okay,
back.
Professor. Okay, Professor. Please carry on. Yeah.
All right.
Good morning, Kalyanam sir. Good morning.
Hello. Yeah. Good.
Good morning. Good morning.
Yeah.
Yes.
Good,
Here is good evening for me.
yeah. Good evening there, Professor.
Yes. Lot of mist around here. So that's
Oh, okay. I don't know. Good morning, everybody. Good morning. Good morning to all. Others will join in meantime. Let us start the program. Now it is time. Tajib sir, please introduce our Professor Kusubovsky and invite for the lecture.
Okay, sir. Okay, warm greetings to all. We have Dr. Thomas J. Kusubowski, Professor to the Department of Mathematics and Statistics, University of Nevada, Reno, with us right now to speak on the topic the classical Laplace distribution, fundamental properties, extensions, and applications. Professor Kusubowski works in the general area of stochastic modeling of natural phenomena in variety of fields, including climate research, geosciences, finance, and economics. His research interest include distribution theory, Laplace distribution and its generalizations, limit theory for random sums, heavy tail distributions, stochastic models for hydroclimatic phenomena, and many more. He has co-authored 2 monographs and over 100 research papers in probability and statistics. Professor Kusubowski is currently an editorial board member of several academic journals and an active reviewer, having refereed for over 100 different academic journals. With the 2016 Sentinel of Science Award, he was recognized by Publons as one of the top researchers contributing to the peer review in the field of mathematics. It is an honor and privilege for us to have you with us today. Once again, I invite Dr. Thomas J. Kusubowski to present the topic.
Well, thank you very much for your kind introduction. Should we get started with the proceedings or what? Can you hear me?
Yeah, Nick, we can hear you, Professor. We can hear you. Now we can start, Professor. It's right time. Thank you, Professor.
Yeah, thank you very much for your kind invitation to participate in the workshop. I'm very pleased to have this opportunity. Thank you. So I will share with you some information about the classical Laplace distribution and various extensions of this distribution. So this is like a survey talk with maybe some new information, but the results are mostly known. So can you remind me how I should get started with the presentation?
Yeah,
How to?
Please go. There is in the bottom. There is an upward arrow. Just to click on that.
The one that says present now?
Yeah, present now. Yeah.
So I'm clicking on the item.
Then there is a small box come up. There is a click in the middle portion.
On the entire screen.
Share button. Okay. And the screen is enough. And the screen. Okay, Professor. Then a small box comes. Yeah, now it is coming.
Something.
We can see the slide. You can move to the slides, Professor.
I should go to my slides, right?
Yeah, Professor. Yeah.
Should I? Do you see them or not?
Yeah, you can see the slides. We can make it full screen, Professor.
I will make full screen. Okay. Do you see them?
Yeah. Now it is fine, Professor. It is fine.
Okay, I cannot see you. You see the slides, right?
Yeah, we can see the slides. We can see the slides and both you also, Professor.
Oh, you also see. Okay, very good. So let me begin then.
Yeah.
Okay, very good. So, so let's see. So let's move on. This presentation is based on work of many people, many researchers, including myself, and in collaboration with various people that are listed here. So my main collaborator is Chris Podgórski from Lund University in Sweden, with whom I have written many papers related to this topic, and also late Professor Katz, with whom we wrote a monograph related to Laplace distribution, as well as many other researchers that are listed on the screen. So the outline of the presentation is here. We would begin with basic introduction to the classical Laplace distribution. We will talk about how this distribution actually comes around and what are the main properties of this classical distribution. We will then move on with extensions, in particular to distributions that are skewed, and also to generalized Laplace distributions. And after that, we will talk about extensions to multivariate distributions that provide generalizations of the classical Laplace, and also mention some extensions to time series and stochastic processes that are built on Laplace distribution, and that would probably be the end of the presentation. we would at the end mention briefly some other extensions and some current research going on in this field. So let's begin then with the classical Laplace distribution. Now, if anyone has questions during the presentation, then I won't be able to see that, you know, like raising hand, because I don't see anything on the screen other than my own presentation. So if anyone has a question during the presentation, please ask, because otherwise I don't know how I can respond. Or of course at the end then there will be questions too, but if you have any questions during the presentation, please feel free to interrupt and just ask a question, okay? All right, so let's move on. We're starting with Pierre-Simon Laplace. Here is a picture of the person. He actually wrote a memoir back in the 1774, where this Laplace distribution actually appeared. And in fact, it was the first continuous distribution with unbounded support that actually appeared in the literature, according to Stigler. The second law of Laplace that today we know as the normal distribution actually appeared later in the same in this memoir, 4 years after that one. Now, one of the earliest sources in which the Laplace distribution is discussed in English is actually in 1911. There was a paper by famous economist and probabilist Keynes that titled "The Principal Averages and Laws of Error Which Lead to Them" was the paper that appeared back in 1911. And in that paper, actually the distribution is derived there as one whose likelihood is maximized when the location parameter is set to the sample median, which is one of the main properties of the Laplace distribution. Now, later in 1923, so we're just going through some historical remarks about the distribution. So it was back in 1923 that Professor Wilson, head of Harvard School of Public Health, actually he noted in his paper published in JASA, First and Second Laws of Error, he noted that good many series of data from economic sources probably may be better treated by the median than by the mean. And he also notes that many data sets from various areas, including economics, biometrics, and so forth, actually fail to conform to the normal law, and he provides examples of data that are much better fitted actually by Laplace distribution than the normal. So he also states the importance of examining the data themselves rather than just forcing, the normal law and its various generalizations upon data for which is actually not fitted. So anyway, moving on, let's take a look at the Laplace distribution and what it is. I'm sure the audience is very familiar with this. So here we're looking at equation number 1, where we present this PDF. F of x is the PDF of Laplace distribution. So actually it's exponential. It's an exponential distribution that is sort of extended to the entire real line. It's a symmetric distribution and it falls down on either side of the mode, which is at 0. And it has a very characteristic peak or sharp needle in the center where the two exponential curves are joined together at 0, but it's not a smooth transition. So it's actually a very sharp peak at the center, very different from what we see in the normal distribution. The characteristic function is also written down below, presented in formula number 2. So again, we have the two main characteristics of the Laplace distribution, and then later, as we speak of various generalizations of this Laplace distribution, then one can either use the characteristic function or the PDF as the basis to extend the distribution, maybe to a skew distribution or multivariate distribution and so forth. So various extensions will be discussed later in this presentation that can be based either on the PDF or the characteristic function of the Laplace distribution. So yes, this distribution indeed has been extended recently to various settings. We're going to go through these in the course of this presentation. So we'll be discussing multivariate extensions, skew extensions, random processes, and stuff like that. The growing interest in this Laplace-based models can be accounted for by fundamental properties the distribution possess. In fact, this sharp peak at the mode is really a characteristic feature that has been observed in many different kinds of data that arise in different fields of applications. One particular area that is commonly seen is financial applications. When you look at various financial data are, actually very sharply peaked at the center due to the fact that many observations in finance are actually very small. Like if you look at stock prices or other assets and how they change over time, then most of the time there is very little change. So there could be large changes, from time to time, but more often than not, the change is a very small one, which explain why so many data values are very close to 0 that actually produce this sharp peak at the mode. Now, the tails of the distributions are still exponential, but a bit heavier than Gaussian. So that's also an advantage of this model that can accommodate data that can fall further away from the mode and accommodate outliers. The moments of any order actually do exist, including the mean and the variance. The distribution is infinitely divisible. That's a very important feature of this distribution, like the normal distribution is infinitely divisible. We'll go over this property later in the presentation. So the importance of this infinite divisibility is actually that it allows extension to stochastic models that are based on this distribution. So some analogs of the Brownian motion, the Levy processes in continuous time can be constructed because the distribution is actually infinitely divisible. Now, there are important properties that relate this distribution to random sums, as we will shortly see. And then there is also various stochastic representations, particularly those that involve normal distributions. So, as we will see, it's a mean and variance mixture of the Gaussian distribution that is a very important feature of this particular model. So random sums actually arise quite naturally in applications, and being limiting distribution of these random sums can explain why these Laplace-based distributions may emerge in particular areas of applications. So in the presentation, we will be reviewing the fundamental properties of this Laplace distribution that would gain some insight into the applicability in many diverse areas. So in particular, we will go over the infinitely divisibility property and extension to geometric infinite divisibility, and also self-decomposability, which are probabilistic properties of this model. So as I mentioned, these properties will lead to development of random processes built on the distribution, and we'll go through some constructions that have emerged in recent years. And we will also discuss how to extend this classical distribution to allow for skewness, multivariate extension, and also, time permitting, we talk about how to extend to heavy tail distributions. So some areas where Laplace distribution comes about are listed on the screen. So I have already mentioned financial applications, modeling logarithmic returns that actually often exhibit such a sharp peak at the center, and have tails that are heavier than Gaussian. These are characteristic features of the Laplace model. So model-based clustering is a very important area of applications, and in recent years we have seen emergence of various distributions going beyond normal distributions. Traditionally, normal distribution is used in this area, but to accommodate skewness and actually to help with identification of outliers, other more heavy tail distributions have been proposed in this area, actually including the asymmetric Laplace distributions, or finite mixtures of this shifted asymmetric Laplace distribution has been a popular model, and among others, such as T distribution. Now, in microbiology, there were some uses of Laplace distribution as well. There's some references that I've listed here, where the skew Laplace distribution is actually emerged. Another very broad area that is very closely related to Laplace distribution is called quantile regression. We will see later in the presentation how this asymmetric Laplace distribution connects with this area. There's actually a very, very broad area, very popular area where instead of predicting the mean of the distribution, we actually use covariates to predict a quantile of the response. And then in this setup, the Laplace distribution arises very, very naturally. Most recent applications that came about have to do with data protection and privacy in statistical databases. Basically, the goal here is to enable the user to retain privacy when releasing information about the underlying population. So typically, when data are released, they have to be somehow modified in a certain way so that information and in this area, there's so-called the Laplace mechanism in differential privacy is a popular method to ensure privacy of when the data are released. So these are just the most recent applications that one can find in the literature connected with Laplace distribution. All right, so let's talk about the ways that this Laplace distribution actually comes about. There are several different ways, as we will see. So first of all, we can think of this Laplace distribution as basically symmetrization of exponential. So we're looking at this stochastic representation in the middle of the screen, where you have exponential random variable e multiplied essentially by the random sign, the random variable I that takes on the values of plus or minus 1. So it's either exponential or negative exponential with equal probability, which essentially extends the exponential distribution to the entire line. All right, so this method of making a distribution and extending a positive random variable to the entire line can actually be applied to any distribution, and such extensions, are very popular with other distributions. We can have an extension of the gamma distribution, Weibull distribution, and a classical distribution that is positive can be extended to the entire line, and so does the exponential. So because of this, the name double exponential is frequently used to describe this distribution. It's basically two exponential random variables put together, positive exponential together with negative exponential with the same scale parameter. So this representation number 4 is indeed very useful when we develop properties of the Laplace distribution. So when we calculate the moment generating function, the characteristic function, the moments, and so forth, all of this is facilitated by this representation number 4. And again, it's one particular way that this Laplace distribution can be constructed. There are other ways that it can be constructed, though. And here is another one. It's kind of surprising because it's actually very, very rare that formula number 5 produces exact same distribution as formula number 4. So when we start with the positive random variable e, we can make a distribution on the real line just by subtracting two identical copies. E1 minus E2 would then be the distribution on the line, which will be also some sort of symmetrization of E. So it turns out that if we take the difference of two exponentials, then we get the Laplace distribution. And in fact, this property is kind of unique to exponential. If we did other types of distribution, not exponential, and we did the same thing, so if we took the difference of two identical copies, if we took the distribution of E and attached the random sign, then the two symmetric distributions would be quite different. And in fact, exponential is the only one where either the difference of exponentials or exponential with the random sign, which we saw in formula number 4, actually produce exact same thing. So another way this Laplace distribution comes about is by difference of two exponentials. Now, the importance of this one is that as a difference of two exponentials, the distributions becomes infinitely divisible, because that's the property of exponential distribution, and the sum or the difference of two distributions that are infinitely divisible is also infinitely divisible. So the classical distribution then of Laplace time has this important property. I would also mention that this type of generalization, where you start with positive random variable and you extend to the entire line, that type of generalization can also be carried out for discrete distributions. And in fact, by taking the difference of two discrete distributions that are positive, we can get a discrete distribution that allows positive as well as negative values. And in fact, such an extension has been carried out for the geometric distribution, in which case we obtain what is called discrete version of Laplace distribution that also is gaining popularity in recent time. All right, so we've seen two types of symmetrization, one by the difference, one by attaching a random sign. Here is another way that this Laplace distribution comes about. Actually, it can be connected with the regression setup. So we're looking at formula number 6 when we have a standard simple linear or actually may not be simple. So classical regression setup where the observation y is related to covariance x through some coefficients beta, regression coefficients, and then on top of that we have some sort of error term. So if these coefficients beta are estimated by minimizing the sum in formula number 7, so these are basically the absolute deviations from the y. We take the difference between the observations y and the linear part, and we try to minimize that sum of absolute deviations. Then the solution that comes about, the estimators obtained in this way actually coincide with the maximum likelihood estimator of beta when we assume that the error terms in formula number 6 have the classical Laplace distribution. So if the errors are Laplace distribution rather than normal distribution, then wherever comes out of this method of absolute deviation from the observations, the estimators that arise in this way are the same ones that the maximum likelihood estimators if the errors are Laplace. So that's another characterization of the Laplace distribution. So after this least absolute deviation, the maximum likelihood produced the same estimator. All right, so moving on, we have another way, quite unexpected way actually, that Laplace distribution is obtained. And here it arises as a scale mixture of normal distributions. So formula number 9 explains what this is. If you take a standard normal random variable z and multiply the standard normal by the square root of standard exponential, then the resulting distribution of x becomes Laplace. So we can think of it as the Laplace distribution is conditionally Gaussian. In other words, if we're given the value of E, then it's a normal distribution with mean 0 and variance sigma squared times E. So because of this interpretation, this variable can be thought of as a normal distribution which has a stochastic variance, and the stochastic variance is exponentially distributed. And this representation is actually, offers a good explanation of why this Laplace distribution arises in certain applications where observations may be coming from some heterogeneous subpopulations that are normal with different variants. This representation 9 can actually be written as well in a slightly different way, where we take the stochastic process B. That stochastic process B is essentially a standard Brownian motion. So it's a Levy process based on standard normal distribution, where at time 1, the value is normal with mean 0 and variance sigma square. And if we substitute for the time t, if we substitute an independent exponential random variable e, so we're basically stopping this Brownian motion at the random time e, and look at the probability distribution of what it is, it's the same distribution as that in formula number 9. In other words, we get the Laplace distribution by replacing t with the random variable e in a Brownian motion. If we replace this e by another random variable, in fact, we can substitute a Levy process that is built on the exponential distribution. The so-called gamma process can be substituted instead of this e. Then we actually obtain another Levy process that is called generalized Laplace process or Laplace motion that we will talk about later on in this presentation. So here's a picture of what the density functions look like of this generalized Laplace distribution. They can transition between the normal that are kind of on the bottom. They can be very smooth normal distribution, and then going through the Laplace distribution when the parameter is 1, and then become very, very peaked when this parameter tau actually increases. Okay, so let us talk about another way that this Laplace distribution can be obtained. And this important interpretation has to do with geometric sums. Okay, so what we're looking at in formula 11 is actually a random sum of random variables. So it's the sum of xj, where the number of terms is from 1 to n, or np, where this np, it's itself a random variable that is independent from those x's, and it has a geometric distribution with parameter p that is written in formula 12. So this object is known as geometric sum or geometric convolution of random variables. So geometric stability is extension of ordinary stability. So a distribution that are stable are those where the sum of n values x1 through xn has the same distribution essentially as x. So an example of stable distribution would be normal distribution, where the sum of normal is normal. Well, sum of the Laplace distribution is not Laplace. However, the geometric sum of Laplace distribution is a Laplace distribution, which is called the stability of the Laplace distribution with respect to a geometric sum. So basically, and there are other distributions that have the same property too, that are more general distributions than Laplace. These are written on the bottom of the screen, formula 13, so-called alpha Laplace or Linnik distributions. They're sometimes called. There is an additional parameter alpha between 0 and 2 that drives this distribution. For alpha equal 2, we get the Laplace distribution, but for other values of alpha, we get a more general distribution.
Professor, kindly unmute the. There is a professor. Professor, please unmute the mic. Hello, Professor Kusmowski. Professor.
Yes, do you hear me?
Yeah, now we can hear.
Can you-
Professor. Now,
So you didn't hear
now we can hear.
anything I was
and
saying? You didn't.
There is some
Okay, let me-
some technical. Yeah, it become muted. That's why. Now it is okay.
I don't understand, but
We can hear you.
did you hear what
Okay,
I'm
bro.
saying or what?
You can continue, Professor, but the slides, you have to go to the slides.
Yes, but were you able to hear me when I was talking or not?
Yeah, yes, Professor.
When I was going through my slides, could you hear me or not?
Yeah, just 1 minute before.
No, it was okay until now. Only very recently it stopped.
Yeah,
Okay, so should I go back to a
Yes.
particular slide
You can
or I
continue,
should
sir.
just continue?
no problem. No problem, Professor. You can continue, Professor.
You are not losing
Okay,
anything.
just-
You can continue.
Going to the presentation. Okay, how do I go back? Let's see.
Professor, you just go to the presentation. Now the slides are not visible in proper way.
Okay, okay, I have to find the presentation. Hold on.
Yeah. You can see the
Just-
desktop. You can see the. We can't see the slides properly.
Yes, and neither can I. I have to find where they are.
Okay. Now it is okay. Oh, sorry, it is not slide. You can go to the slides,
Yes.
Professor. Yeah.
Yes, that's what I'm trying to do.
Okay.
Hold on, this is what I'm trying. Please bear with me, okay?
No problem, Professor. It's technical.
I have to find them, okay? I don't know what happened. Just a minute.
Yeah.
Do you see them now or not?
Now we can see the slides from the first page onwards. Can make it full screen and go to the consent pages.
Gosh,
Maya Chowdhury, why you have raised the hand?
just a minute. Give me a moment. I'm trying to
Sure.
maximize. For some reason, I cannot make them larger. I don't know what's going on.
Hmm?
Okay, is it
Yeah,
better?
that is fine. That's fine. Now it is fine. We can see can go to the consent. Yeah.
So I'm going through. Okay, so should I begin here, or here?
Figure. Okay. Now that's a position.
So let me briefly recap this. I was talking about the stability property, right? With the geometric sum, where you have the sum of x's is equal to this s. And the property says that if n is geometric and x's are Laplace, then the sum is also Laplace. So basically, the geometric sum of Laplace is Laplace. The Laplace distribution has the stability property with respect to geometric sum. There are other distributions that have the same property, like in positive distributions that would be exponential, and also these Mittag-Leffler distributions that are given by the Laplace transform in Formula 14. Now, the stability property is really an interesting one when you're talking about exponential distribution, which is the absolute value of the Laplace. This stability property can actually be seen in actual data. For example, when you look at the financial data, maybe currency exchange rates is a particular example that have been studied. So what's going on here is that you're looking at, like, say, daily observation. This RJ could denote, let's say, an exchange rate, foreign currency exchange rate on day J. And basically, we're looking at how this value changes from day to day. So we can look, it's common to look at logarithmic returns, where you look at the log of the ratio from 2 consecutive days, or all the log of Rj plus 1 minus log of Rj is the change from day to day. So basically, when you look at these things, it's interesting to check the consecutive days where the prices or the exchange rates are moving up or down. So the RJ may be going up or may be going down from day to day, and you're looking at the period where the price is increasing or the period when it's decreasing, and that can be captured by the stability property. So basically, the return over a single day can have the same distribution as the total return over the growth period. And that is actually something that can be seen in actual data. So there are some references that are listed here that discuss this interesting property. Now, as far as the geometric stability and sums, one can say that this Laplace distribution is not only stable with respect to the sum, but also approximates the random sum of any random variable. So basically, if you have a random sum of geometric type of some random variable x, and those x's are symmetric random variables, then when this n is very large, so if it's a geometric random variable with small p, so that the sum then can be approximated by the Laplace distribution. So it's sort of property very similar to normal distribution, where normal distribution is also commonly used as an approximation to sums of random variables. So similar property is true for Laplace distribution, that Laplace distribution approximates sums of geometric type when there is a random number of terms in the sum and it has a geometric distribution, then Laplace distribution is commonly used to approximate those. So here is a visualization of how random sums are different from regular sums with the fixed number of terms. So let me explain what we are looking at. In the histogram on the left-hand side, the very first one, we're looking at distribution of randomly generated sums, where each sum actually has 100 terms, and the values in the sum are IID uniform random variables from -1 to 1. So we're looking at the sums of n uniforms, and because of the central limit theorem, the sums of 100 uniforms actually look like normal distribution. So that's the picture on the left. On the other hand, in the middle, we're looking at the geometric sum of the same uniform. So we still have uniform random variable from -1 to 1, but this time the number of terms in the sum is actually not a fixed n, but it's a geometric n with mean equal to 100. And the distribution is quite different from normal. It already has this characteristic peak at the center, and the tail is a little bit more heavy. And the one on the right, that's also a random sum. That one has a different n, not a geometric n, but a different random variable n. Actually, it's a discrete Pareto random variable, also with the mean equal to 100, and the peak is even more pronounced. So generally, the lesson we're learning from this is that when we deal with sums of random variables, and it's not necessarily a deterministic sum, but the number of terms is also random, the normal distribution typically doesn't approximate the sum. There are other distributions that do. And in fact, Laplace distributions are ones that approximate the sum when the number of terms is a geometric one. As far as the statistical issues go, then estimation for the classical Laplace is pretty straightforward. One can do maximum likelihood estimation. As we know already, it was mentioned that the maximum likelihood estimator is basically the median of the random sample, and the scaling parameter can also be estimated explicitly in formula number 18. So there's no major issues with estimation of Laplace, and the estimators have standard properties. They are consistent, asymptotically normal, and efficient. And you know that there are many papers that deal with the estimation of the Laplace distribution and goodness of fit testing and so forth. So let me move on now with the next extension, how we can extend this Laplace to skew distribution. When we're extending to skew distributions, that there are many techniques of extending to the skew one, and let me mention a couple of them. So one particular extension that is very popular in recent time was the similar approach that was used by Azzolini in 1985 when he introduced the so-called skew normal distribution. So this type of extension became very popular, and many symmetric distributions have been generalized through the scheme. So basically what it is, you start with the distribution that is symmetric. It has a PDF F. This F could be a normal distribution, could be Laplace distribution, could be some other symmetric distribution. And the capital F is the CDF of that distribution. And it turns out that if we multiply this PDF by the CDF, where in the CDF we put additional parameter like a scaling factor lambda, which is a real number, then we actually obtain a genuine PDF through this scheme. We have to multiply by 2 to ensure it integrates to 1. And it's some sort of skew distribution that generalizes the original distribution. So if the F here connects with the normal distribution, then we get the Azzolini's skew normal distribution. And we can also do the same thing with the Laplace distribution. And when we do, we obtain some sort of skew version of the Laplace distribution. So while this skew Laplace distribution obtained in this way is actually infinitely divisible, which is a nice property, but many other properties of Laplace distribution don't hold for the skew version obtained through the scheme. So there are other ways to introduce skewness that are more natural and lead to different versions of skew Laplace distribution. which is the version that we will focus on. So the version that we will focus on as far as the skew Laplace distribution is the version that is obtained by generalizing the characteristic function of the Laplace distribution. So here we're looking at formula number 20. On top of the screen, we're looking at the characteristic function there. If we didn't have the term connected with mu, so if that mu was equal to 0, then it reduces to the classical Laplace distribution that is centered at theta. Now, by introducing mu, we actually get some other distribution that is more general. And in fact, that's the skew Laplace distribution that we will study. So this particular generalization has been referred to as the asymmetric Laplace distribution with parameters theta. So theta is the mode of the distribution. In fact, there is a scaling factor and there is parameter mu. Okay, now it turns out that this particular characteristic function actually can be written as formula number 21, where the quantity phi under the log, this phi of t, is actually the characteristic function of the normal distribution with mean mu and variance sigma squared. So if we take the characteristic function of the normal and take the log of this characteristic function and put it in formula 21, then it leads exactly to formula number 20, which is what we call the skew Laplace distribution. And this type of characteristic function 21 actually is the one that corresponds to the distribution that is a limiting distribution of the random sum in formula number 22. So if you have any random variable xi that are IID and have finite variance, and NP, the number of terms in the sum, is an independent geometric random variable. So when this NP is very large, when P converges to 0, if this random sum converges to any distribution, then this distribution must be of the form number 21. So this is due to the classical results in probability theory. There's some references provided later in this presentation, and then also at the back, that the random sums, if they converge to anything, then they have to converge to this right here, where this phi is the characteristic function of the normal distribution. So because of that, that's precisely how this leads to the formula number 20, which is what we call asymmetric Laplace distribution. So to summarize this asymmetric Laplace distribution actually comes up very naturally as the limiting distribution of random sums with geometric number of terms when the terms in the sums have finite variance. So it's sort of analog of normal distribution for the random variables with finite variance, and what distribution approximates the sum if the number of terms has a geometric distribution. So there's further discussion about this here. Again, we're looking at this equation in a slightly different way. So here we can connect it with the Laplace transform number 24 of standard exponential random variable. And in fact, when we take this into account, it can be shown that this Laplace random variable x can be written as B of E, where B is now again a Brownian motion, but this Brownian motion actually has a drift. So it's a Brownian motion where the value at 1 is a normal distribution with mean mu rather than mean 0. And if you substitute for t in this Brownian motion an independent exponential random variable, then that's how you get this asymmetric Laplace distribution. So it follows that this asymmetric Laplace distribution is actually what is called the mean variance mixture of normal distribution. So a mean variance mixture of normal distribution generally follows the representation given by equation 26, the one on the bottom of the screen. So what we have here is the standard normal random variable z multiplied by square root of e, and then on top of that we add on another term that has to do with the exact same e, so which is also exponentially distributed. And this additional term that is in the middle on the right hand side actually makes the distribution skewed. So the skewness of the distribution has to do with this mu. If mu is equal to 0, then the distribution is a symmetric one. And for different value of mu that is not equal to 0, we get a skew distribution. Okay, any questions at all? So again, in this more general construction here, we can substitute for the random variable e, we can substitute another random variable, and whatever random variable we substitute for the e, we always get another mean variance mixture of normal distribution. So this e can be any random variable that is positive. It could be gamma distribution, Weibull distribution, any positive distribution can be substituted here in this Brownian motion with drift, and we always get some sort of mixture of normal distributions. In fact, we can substitute for this E a stochastic process, a gamma subordinator that was mentioned earlier, and when we do that, then we get a stochastic process called asymmetric Laplace motion, and the marginal distributions of this stochastic process are what we call generalized asymmetric Laplace distributions, or GAL. Now, in order to calculate the density of this asymmetric Laplace distribution, it's convenient to introduce another set of parameters. So in fact, when we denote by kappa, it's another parameter that we can relate to sigma and mu through equation number 27, that is a number between 0 and infinity. So by means of the parameter kappa, we can actually write this density function in explicit way. So that's the density function number 28. In the middle of the screen is the density that corresponds to the characteristic function that we saw earlier. So as we can see, actually we're looking at some sort of exponential function here. So there is exponential function for x is greater than theta, and another exponential for x is less than theta. And the difference is that the two exponential functions have different scaling factor, where one has kappa in the numerator and the other has kappa in the denominator. So it's two exponential functions essentially put together with different scaling factors. So it can also be shown that this PDF actually corresponds to the difference in formula number 29. So by taking the difference of two exponential random variables that have different scales, So one exponential is multiplied by kappa and the other is divided by kappa. So they are different exponentials now. When we put them together and take the difference of the two, we get the probability distribution with density 28. All right, and again, there is a discrete version of this distribution too called discrete asymmetric Laplace. The scheme that leads to the Laplace distribution of the skew type is actually a generic one. It can be applied to any random variable. It was introduced in 1998 in a paper of Fernandez and Steele. So they discuss how one can introduce skewness into a symmetric distribution. So what is happening here is when you have a PDF G that is a symmetric PDF on the real line, we can actually construct a skew distribution by means of formula number 30. So we put different weights for on each side of theta. Basically, for x is greater than theta, we multiply by kappa. For x is less than theta, we divide by kappa. And then we have to figure out the appropriate norming constant that make the PDF integrate to 1. And the construction is very, very general and can be applied to any symmetric distribution. And indeed, it has been applied beyond the Laplace distribution to obtain many skew distributions that actually follow this construction. This density in 30 can also be connected with the stochastic representation down near the bottom when we have a random variable W multiplied by an independent random variable I. So the independent random variable I essentially takes either negative or positive value. I think that one of these values should have been 1 over kappa, maybe negative kappa and 1 over kappa, I think, with different probabilities. So it leads to a skew distribution with PDF given by 30. And stochastic representation is actually quite useful when we want to develop further properties of this distribution. Now, log Laplace distribution is another type of distribution that is closely related to this. It's an analog of log normal distribution. So basically, it arises by taking when we take exponential of the Laplace distribution, we get the log Laplace distribution with density given by equation 31. I think I have to maybe skip some of the slides if I want to get to something else. Let me talk about a relation to quantile regression. So quantile regression is a very powerful tool that emerged in recent time when dealing with, with covariates and how to use them to predict the quantile of the distribution. So generally, in the standard regression setup, one may wish to minimize the following function of beta. So there is this so-called check function rho q under the sum. This check function is explained in the middle of the screen. So we're looking at this quantity here. So basically, it's either a positive part of U or negative part of U, but taken with different weights. So U plus, it represents the maximum of 0 and U. So for positive U, it becomes U. And for negative U, this u minus takes over, and it's a negative u. So it's kind of extension of absolute value. You can think of an absolute value function, but with different. So you have two lines that meet at the origin, but the two lines have a different slope. So on positive half line, the slope is q, and on negative half line, the slope is 1 minus q. So there's like absolute value with the negative slopes on either side of the origin. And if q is equal to 1/2, then this function is just the absolute value function. Other than that, it is this more general check function. So it turns out that simple algebra will show that minimizing this particular function with respect to beta is actually equivalent to finding the MLE, maximum likelihood estimator, of the parameter beta, if we assume that the error term in the standard regression setup, instead of being normal, actually follows this distribution that is written on the bottom of the screen, where the check function, in fact, appears in the PDF of the distribution in the exponent. All right. However, this PDF on the bottom of the screen is actually the asymmetric Laplace distribution. So in a nutshell, the connection between this asymmetric Laplace distribution and quantile regression is that the estimates obtained in quantile regression are the same estimates that one would get if they assume that the error in the standard regression setup actually followed asymmetric Laplace distribution. There is a very close connection between the two notions. Now, it's also worth noting that if we have a data set, if the yi's is just a set of data and we try to minimize the quantity on the bottom of the screen with respect to theta, then what we get out of this is actually the qth sample quantile of the data set. So that provides another motivation for calling this quantile regression, because this check function is closely connected with sample quantile of the random sample. So here we're looking at generalizations of this Laplace distribution to generalized asymmetric Laplace distribution. So this generalizations comes about by taking the Laplace characteristic function and raising to arbitrary power tau, which is a positive number. Because the distribution is infinitely divisible, we can actually do that and obtain a more generalized distribution called GAL, or generalized asymmetric Laplace distribution. That one is also the scale and mean mixture of normal distribution given by formula number 20, where the random variable G is actually a gamma random variable. So in financial literature, it's a very popular model that is called variance gamma distribution, or more generally, variance gamma stochastic process. Here are the sample density function of this generalized asymmetric Laplace distribution. And then there is property of geometric infinitely divisibility too. The distribution can be broken or down into these factors. We can break X into the sum of NP components, where these x's are independent and they follow another distribution. And if we can do that for each and every p, between 0 and 1, then the distribution is called geometric infinitely divisible, and it follows that the asymmetric Laplace distribution actually does have this property of geometric infinite divisibility, and the terms in formula 41 on the right hand side are also themselves a symmetric Laplace distribution. They have the same type of distribution as well. So I will have to skip probably for some of this stuff, because we're getting close to the presentation, right? How much time is there? Do I still have any more time at all, or is it over?
5 more minutes, sir.
5 more minutes. So let me say a few words about multivariate distributions. For the multivariate distribution, we can generalize in many different ways. You know, going from one dimension to multivariate distribution, there is not, more than one path to do that. The problem is how to do it so that we extend major properties of the distribution, right? That's the main thing. Here is one generalization that uses the PDF of the Laplace distribution to get a distribution that is multivariate. That distribution has formula number 50, but it turns out that this distribution actually has very little to do with the Laplace distribution. The only thing in common with Laplace distribution here is that when the dimension is 1, it becomes the Laplace distribution. But for the multivariate distribution, it actually has nothing to do with Laplace distribution. The one-dimensional distributions, for example, are not even Laplace. So a more natural extension to get multivariate distribution is by using the characteristic function. We're looking at formula number 52. This is in the symmetric case, the characteristic function of symmetric Laplace distribution. And formula number 53 is the characteristic function of asymmetric multivariate Laplace distribution. And it has many properties that are very, very similar to those of the Laplace distribution. So all marginal distributions are of the same type. All univariate marginal distributions and multivariate distributions are the same kind of distributions. Or linear transformation of multivariate asymmetric Laplace are also asymmetric Laplace. The stochastic representation in the middle of the screen is very similar to one-dimensional stochastic representation. So the only difference is that X now is the multivariate normal distribution multiplied by the scaling factor. And then there's additional factor mu times W that makes the distribution skewed. So these are all mixtures of Gaussian distributions. These distributions are all infinitely divisible, and they can be now extended to stochastic processes that are multivariate and based on the asymmetric Laplace distribution. Here's the example of densities in the bivariate case. So an extension to generalize asymmetric Laplace distribution is also possible. It's through the characteristic function in formula 55. The somewhat difficulty with working with this distribution is that the PDFs given by equation 56, they are semi-explicit. So, it's a computational formula that depends on the special function K. That's the modified Bessel function that has integral representation. So it's possible to work with this, but it's not very convenient for doing parameter estimation. And in fact, for this type of distributions, maximum likelihood estimation is often carried out by means of expectation maximization algorithms. They work very effectively. in this setup. So I guess I will. I don't have time to talk about stochastic processes, so I will skip through this and just make some conclusions about the extensions. So I guess, yes, I probably will just finish with this one. So, so there are many different ways of extending the classical Laplace distributions. We've seen extension to skew distributions, we've seen extensions to multivariate distributions. I mentioned stochastic processes of Laplace type. So extensions have been made in this area as well. One can study mixtures of univariate and multivariate Laplace distributions, which is closely connected with random summation scheme. This is some of the current work that I'm doing. There are also extensions to matrix-valued Laplace distributions, which is another recent work in this direction. So I will actually talk about that one, matrix-valued Laplace distributions, at the conference you said on Saturday. So I have another presentation on that. So with that, I think I will have to stop this presentation. There's also something else I wanted to talk, but I overestimated my time. So there's some references at the end. If you're interested, I can just flash through some of them that relate to the topics that were discussed today. And then I thank you for your attention, and I will conclude my presentation with the references and the thank you. Hello, can you hear me? How do I go back to the... Okay, here we go. Do you hear me?
Yes, we can hear.
Okay. So I'm done with the presentation. Thank you.
Okay, can you hear me?
Yes.
Hello?
Yes, I can hear you. Are there any questions? Yeah, maybe you cannot hear me. I'm not sure. Let's see. Can everyone? So what's happening? Are there any questions? Can you hear?
Yeah, we can hear you, Professor. Any questions, please? One question, there is time for one question only, because the next speaker is also ready to start at 10:20. I think Professor Bala has to say something. Hi, Professor.
Bala, sir.
Oh, thank you for.
Yeah.
I hope that it.
If there is no question, yeah, Professor Bala, do you want to say anything? As just unmuted? No. Okay. Now let us move to the next session. In fact, we have a wonderful talk by Professor Kusubowski. He covered several ideas on the Laplace distribution and its related families of distributions. And we are very much thankful to you, Professor. We extend our gratitude to you for your support to our activities and your deliberations. Thank you, Professor. Thank you so much. Now,
Thank you.
Thank you. Thank you, Professor. Now let us move to the next speaker. Professor Debashish Kundu is here, ready to speak. Tajunisa, please briefly introduce Professor Kundu and invite him for the talk.
Okay, sir. Hello, everyone. Now we have Dr. Debashish Kundu, Professor to the Department of Mathematics and Statistics in the Institute of Technology, Kanpur, India, with his talk on geometric skew-normal distribution. Professor Kundu is interested in the domains of statistical signal processing, nonlinear regression, survival analysis, generalized exponential distribution, as well as statistical computing. He has presented several papers in various national and international conferences and workshops, including at the 9th International Statistics Day Symposium in 2014 held at Antalya in Turkey and the Indo-Russian workshop held at the Indian Statistical Institute, Delhi in 2015. He has more than 300 published research papers to his credit, including exponentiated exponential distribution published in the Encyclopedia of Statistical Sciences in 2004 and a bivariate inverse variable distribution and its application in complementary risk model published in the Journal of Applied Statistics, Volume 47, 2020. With great pleasure and honor, once again, I invite Professor Debashish Kundu for the presentation. Over to you, sir.
Okay, thank you. Let me just try to share.
So you please go to the slides, Professor.
Yeah. Yeah. So can you see?
Yeah, now it is coming, and now it is fine, Professor. Fine.
It is okay?
It's okay.
Okay. Okay. So yeah, thank you for the kind introduction, and thank you for giving me the opportunity for speaking on this issue.
Excuse me, please mute Rasul. Yeah, please. Professor, please.
Yeah. So the topic of my presentation today is on the geometric skew normal distribution. And well, I mean, since it is a workshop presentation, so I will request that if you have any questions or doubt, just don't hesitate to stop me in between, so that we can have a we can clarify the matters as we go along. Okay, and this is the brief outline of my talk. So first, I will briefly mention about some of the drawbacks of the normal distribution, and then one of the famous the skew normal distribution, which was introduced by Azzolini. So I will briefly mention about that, how some of the drawbacks which have been which are present in the normal distribution can be taken care of. Then another distribution which is in the skewed form, which is known as the power normal distribution. I'll briefly mention about that one also. Then we'll talk about whatever our main topic is about the geometric skew normal distribution. We talk about some of the multivariate generalization of the geometric skew normal distribution and some related models and some of the open problems which will come along that line. Okay. So yeah, so let's start with the normal distribution and some of the well-known drawbacks of the normal distribution. See, I mean, in most of the times, we feel very comfortable of analyzing the data based on the normal distribution because of its in a compact form about the estimators and I mean all those nice properties. I mean, extensive work has been done about the normal distribution, but often what it can happen, suppose your data indicate that it is not symmetric, okay, or suppose it shows that it's an heavy tail, I'll mention what do you mean by the heavy tail one. So suppose it's an heavy tail, it's not symmetry, or even suppose it is not unimodal. Okay, so because we know that the normal distribution has all these properties. That means it is a symmetric one. It is what we call as a lighter tail, and it is an unimodal distribution. Okay, so so suppose our data indicate, the preliminary data analysis indicate that, well, at least one or more than one properties it is not satisfying. Okay, and whenever we are talking about the symmetric one, I mean, we are talking about, say, there exists a mu such that the probability density function is of the form of f of mu plus x is equal to f of mu minus x. By the way, in my talk, in this talk, we will be restricting ourselves about the absolute continuous distribution. So which basically means that there exist density functions. Okay, so we are not going to mention it again and again, but that's what we'll be assuming, that whatever we'll be talking about, which is an absolute continuous distribution, which has a proper density function. Okay, so yeah, so whenever you're talking about the symmetric one, which basically means that symmetric about a particular value of mu, so which need not be a mean because mean may not exist, but at least we can say that it's a location parameter. So f of mu plus x is equal to f of mu minus x. And suppose your data indicate that, well, it is not satisfying this particular property. Okay, or suppose you are looking at the tail behavior of the distribution. I mean, which is basically that for large x, I'm looking at probability that x greater than x. Similar thing I can think about the probability x less than minus x. Okay, for x greater than 0, and which is in the form of capital O of 1 minus capital phi of x. This capital phi is simply nothing but the distribution function of the normal distribution. So 1 minus capital phi of x, so which is approximately equal to the order e to the power negative x squared by 2 by x. Okay, so what will happen that your the tail behavior probability x greater than x, which is greater than that. Okay, so that the probabilities are more than that quantity. Okay, so that we call as the heavy tail one. Okay, or suppose the data indicate that it has a multimodal. Okay, so which might have more than one mode. I mean, maybe 2, maybe 3, or maybe even more. Okay, so what will happen that if the things are like this? Okay, so to overcome some of these issues, it's a very I think the genius way, interesting way, Azzalini introduced what we call as a skew normal distribution. Okay, and this is basically the general goal when we are trying to move away from the normal distribution. So we want to generate a non-symmetric class of distributions which have support on the whole real line, and that is important actually, because we know that if it is on the because there are all the distributions which are available on the positive real axis 0 to infinity, it simply cannot be symmetric. It has to be skewed. But here the idea is slightly different. Here we are trying to obtain a non-symmetric class of distributions which is on the entire real line. Okay, just like the normal distribution which is symmetric over the entire real line. So idea is that to generate a non-symmetric class of distribution on the entire real line. The second one is that what we want that it's a class of distributions, but what we want that a normal distribution should be a special member. And the whole idea behind it is that because when you try to fit the data based on this the general class of distributions, then at least that data should speak in the sense that, well, whether it is coming from a normal distribution or not, that I think we should be able to test it based on the data. And if a normal distribution is a special member, so clearly it is due to some of the parameters, some particular values of the parameters, it will take the form of the normal distribution, and therefore definitely we should be able to test whether the data justifies the away from normality or the data does not support moving away from normality. So that's the reason this one that we want to obtain the normal distribution as a special member of this class. Okay, and of course at the end it should not have too many parameters. Okay, because again, I mean, if you have too many parameters in the model, clearly it will be very difficult to justify, or people may not like it actually. And whenever we are talking about the too many parameters, because we know that the normal distribution has two parameters, and we want that this particular class is a more general class which has the normal distribution as a special case. So we can expect that there should be at least three. Okay? So there should be at least three parameters in the model. Okay, so that is basically the whole goal about this generating the this class of distribution. And this is basically the construction, which is a I think it's a very interesting constructions in a very genius way, but very simple. I mean, that is the most important part. And the way it has been done, it is that you are looking at two different random variables, x and y, two independent random variables, standard normal random variables, and take any lambda, any real number. It can be either zero, it can be either positive or negative, or it can be zero also. Okay. So what you're looking at, if the probability x is less than lambda y. Here, remember that x and y both are standard normal, they're independent, so which turns out to be that probability x minus lambda y, which is less than zero. And clearly, x minus lambda y is a normal random variable with mean zero and variance 1 plus lambda squared. Therefore, your probability x minus lambda y, which is again symmetric about zero, so probability x minus lambda y less than zero, that becomes equal to half. Okay, so that is one of the nice equality what we have. So now let's try to write down the probability x minus lambda y less than zero in terms of the density function and the distribution function of x and y, because x and y are two independent standard normal random variables. So let's write down the left-hand side of the probability that x minus lambda y less than zero in terms of the density function and the distribution function. And that's what it is being written, that if you're looking at this probability that x less than lambda y, which is simply nothing but, for a fixed y, it is capital phi of lambda y and small phi y dy, and small y can take the entire range minus infinity to infinity. Okay, so that gives you that the probability x minus lambda y less than zero, which is simply nothing but the integration of the capital phi of lambda y in small phi of di. Of course, this capital phi is a distribution function of a standard normal, and the small phi is the associated density function of the standard normal one. So therefore, what you obtain, one side, we got that probability that x less than lambda y equal to half, and the other side, we got that capital phi of lambda y, small phi of dy, and therefore half equal to the integration of capital phi of lambda y in small phi y dy. Okay, so now that's a very interesting thing. So what you can see that the right hand side, the capital phi of lambda y and the small phi of dy, everything is non-negative. So therefore capital phi of lambda y, small phi of dy. If I make it a proper normalizations, what we can make it simply 2 times that, so that becomes a standard probability density function. Okay, and that is precisely the Azzolini who has defined this, and he called this one as a skew normal density function. And as you can easily see from here, that if you put that lambda is equal to 0, then your capital phi of 0, which becomes equal to half, and therefore your density function of the skew normal density function becomes the standard normal density function. Okay, so whatever we want to achieve, that means that, well, we want to have a class of distributions. Okay, what we call this one as the class of skew normal distribution function. Okay, which is parameterized by the lambda, what we call sometimes the skew parameter, and so that's what it is. Interesting thing is that, well, you can see that actually there is nothing special about the normal distribution. I mean, actually, you can take any symmetric kernel there, okay, over the entire real line, and you can do the same process actually. Should not be any problem at all. But anyway, let's stick to the normal distribution in this case, because that's what we are interested in. So this particular one is called the skew normal with parameter lambda. Okay. So let's look at a couple of pictures, and as you can see that if you take lambda positive, if you take say lambda is equal to 5, it becomes a positively skewed, and if you take a lambda negative, it becomes a negatively skewed. And of course, if you take lambda is equal to 0, it becomes symmetric, and that becomes a normal distribution. Okay. So there are a couple of very, very interesting properties of this one, and some of the properties, as I had already mentioned, that your Sn0 is a density function of the normal 0, 1 that I had already mentioned. So that becomes a special class, and that is precisely what I was trying to mention at the beginning itself. That means that suppose I am trying to analyze a data set based on this skew normal density function, and therefore very well I can go for a testing lambda is equal to 0 to identify whether the data are coming from a normal distribution or not. Okay, so that's what I think that's what I meant when I say this one, that at the beginning itself, that the data should speak. Okay, some of the simple things, that if Z is a skew normal, then if you're looking at the minus Z, that is also a skew normal with parameter minus lambda. Okay, so that can be easily seen. The PDF of the skew normal is unimodal. Okay, that is simply there. And if Z is a skew normal one, we have a simple thing what we can obtain, that Z squared, which is a chi-squared one, which is the same thing as the standard normal. Because if you remember that, well, if you have a standard normal Z, then the Z squared is a chi-squared one. So in this case also, it doesn't matter what is your lambda, all the times your Z squared becomes equal to chi-squared. These are some of the simple but the nice important properties. Let me just mention that, well, if you have this, you suppose you use a normal 0, 1 and a variable, then for any constant h and k, the expected value of this becomes equal to this, and therefore the moment generating function of z, which can be easily obtained in terms of the distribution function. Okay, and of course the moment generating function helps us because it helps us in the characterizations, it helps us in deriving different moments and all these things, which can be easily obtained, and we'll just present the moment generating function of the different moments. So for example, the mean of this becomes equal to beta delta, and the variance becomes 1 minus beta delta square, where beta is simply, it's a simple exercise actually. Okay, so in summary, what can be seen as this skew normal distribution, that, well, it can be skewed, as we have already seen, that for lambda positive, it's a positively skewed, for lambda negative, it becomes a negatively skewed. What we have seen that the normal distribution is a member of this class, of course, that we have seen that for lambda is equal to 0, the normal distribution is a member. It is always unimodal. Okay, it is always unimodal. Fourth one is that it cannot be heavy-tailed, and well, I mean, we have not shown anything here, but what can be shown here, that it has the same thickness as the standard normal density function. So therefore, it is not a heavy-tailed distribution that is there. But another important thing is that the multivariate generalization can be obtained along the same line. It's not too much of a problem. We can easily go along following the similar procedure. We can obtain the multivariate generalizations. Okay. So before coming to the data analysis, I just want to mention one thing. So you can see that here this Azalin's skew normal density function. Of course, it is a general class. You can obtain the normal distribution as a special case. That's what we are looking for. Yeah, that is there. But we cannot have a multimodal density function. That we cannot have. and we cannot have a heavy tail one. Okay, so these are the positive and the negative points about the skew normal distribution. So if you remember that we had given goals, 3 goals we had given, we can satisfy 1, but the 2 of the goals we are not able to satisfy. Okay, so now let's come to the data analysis of the skew normal distribution. So I mean, it is very natural that unless we can develop a very I would say it's a convenient estimation procedures of the unknown parameters. I mean, whatever way it is, it will be very difficult to use it in practice. Okay, so naturally that it's a very natural thing that we like to have this the scale parameter and the shape parameter also in the model, and that can be of course easily introduced. I mean, we can easily introduce the location parameter mu, which is x minus mu, just replace x by x minus mu, and we can introduce the scale parameter, which is sigma, which is x minus b by sigma. Okay, so as you can see that if you put lambda is equal to 0, that becomes the standard normal with the mean mu and the variance sigma square. So boils down to the same thing. So this is the model when we have the location as well as the scale parameter. Of course, the skewness parameter is also there, which is lambda. Okay, and this is the density function. So extensive work has been done about the maximum likelihood estimators. I mean, of course, you have to solve 3 unknown equations, nonlinear equations, but people have used the EM algorithms and all these things. So I mean, yeah, it's quite a bit of work has been done along this line, because it becomes a very popular one. So the standard procedure, but there are certain issues about these maximum likelihood estimators of the skew normal distribution, and this is one thing we have to keep it in mind, that the MLEs may not always exist. Okay, so that actually has been shown even by Azzalini also, that MLEs may not always exist in case of the skew normal distribution. In fact, what it can be shown that if all the data points are of the same size, the MLEs do not exist. And whenever we are talking about the MLEs do not exist, which basically means that along a particular path, the log likelihood function can keep on increasing. Okay, it's a monotonically increasing function, so it does not have a maximum within the parameter space. Okay, so that's what it means, and that's what Azzalini also has mentioned. And therefore, what we can see that, of course, there is always a positive probability that the MLEs do not exist. And not only that, the second point is also that what is also another important point, that for certain range of the parameter values, the Fisher information matrix is very unstable. And whenever you're talking about the very unstable one, what it means that it's a very close to the singular matrix, which basically means that one of the eigenvalues, one or more than one of the eigenvalues, are very close to 0, and therefore the calculation of the inverse, it's a very unstable one, and the construction of the confidence interval may not be very easy based on the Fisher information matrix. Okay, because that's what we use. So that becomes a difficult one for certain range of parameter values. Okay, so we need to be careful when we try to use these things in practice. Okay, so this is one of the problem about this skew normal distribution proposed by Azzalini. Okay, there is another one which is also again trying to take care about the goals what he had mentioned, which is known as the power normal distribution. And the power normal distribution, I mean, let's go back. I mean, this is a very general construction, and it has been done for many other distributions, and in this particular case, what it is called as a power normal, or sometimes it is the exponentiated normal one, and which is nothing but you write down the distribution function of a random variable x, fx, as capital Phi x to the power alpha. Okay, where capital Phi x is the distribution function. Okay, so capital Phi x to the power alpha, capital Phi x is the the distribution function of the standard normal distributions. Okay, so now if you look at this fx, which of course it can be easily seen that it's a proper distribution function. Okay, it can be easily seen, this one actually, for any distribution function capital fx. For any distribution function capital fx, capital fx to the power alpha for alpha positive is always a proper distribution function, and that can be easily seen that fx is a non-decreasing function in -∞ to infinity, because fx is non-decreasing, fx to the power alpha is also non-decreasing. Since fx is right continuous, that phi x to the power alpha, that's a way. So all those properties, because of the properties of the capital phi, that f will satisfy all the properties of the proper distribution function. So that is a proper that's a proper distribution, and therefore we can have a proper density. It's an absolutely continuous. I mean, that's not a difficult to see. And what we have, the density function also is in a nice form. So the density function, my f of x, which turns out to be alpha times phi of x, which is the standard normal density, and capital phi of x to the power alpha minus 1. Okay. So this is basically the density function of the power normal distribution. Okay, and let's look at a couple of pictures of the density function of the power normal distribution, and what you can see that, well, it can be symmetric. Okay, it can be symmetric, and as you can see that if you put your alpha is equal to 1, because your f of x is capital phi x to the power alpha. Okay, and that you can see that if you put alpha is equal to 1, and then f of x becomes equal to phi of x. Okay, so that's what we have it here. Okay, so you can see that if you put alpha is equal to 1, your f of x becomes equal to phi of x, and therefore the standard normal is a special case of this class of distribution. So, and actually, if you put your alpha is greater than 1, then it becomes a positively skewed, and if your alpha is less than 1, then it becomes a negatively skewed. Okay, so that's what it happens. Okay, so of course, similar to the skew normal distribution, what are the things what we can see it here? Well, you can see that normal distribution is a special case. That means in this particular case, suppose we try to fit the data based on the power normal distribution, and we want to check whether it is coming from a normal distribution or not. So naturally, my testing can be alpha is equal to 1. So again, as I mentioned before, the data should speak. So based on the data, I should be able to decide whether it is coming from a normal distribution or from a skewed distribution. And of course, if alpha is greater than 1, the data basically indicate that the positively skewed or the negatively skewed, and those things can be easily done based on the testing one. Okay, here also the probability density function is always unimodal. Okay, just like the skew normal distribution as proposed by Azzolini, in this case also the probability density function is always unimodal. That is there. And it can be both positively and negatively skewed. Okay, same thing like the Azzolini skew normal distribution function. And so therefore, what you can see that the power normal distribution has many properties which are very closely associated. I mean, they are very close to the Azzolini skew normal distribution. Okay, all these things. I mean, it's a normal distribution is a special case. The probability distribution is always unimodal. It can be both positively and negatively skewed. And but the fourth one is an interesting one, because if alpha is an integer value, the different moment can be expressed in explicit forms. Okay, so that is one of the nice part about the power normal density function. Okay, but again, similar to the Azzolini's skew normal density function, it can be seen that it cannot be Hebbian. Okay, so it has the same it has basically the same thickness as the normal distribution, so it cannot be heavy-tailed here also. Nice part is that all the moments are finite. There is not a problem at all, and the multivariate generalizations has also been done. Of course, it need not be unique. It can be done in a several way. One of the ways which has been done by using this skeletal copula. Okay, and some of the nice properties and all these things which can be developed, and because of this copula structure, I mean all the different association properties, all these things can be developed. But again, this generalization is not unique, and we know this one, that I mean whenever we'll be going from the univariate to the multivariate case, I mean there are different ways of generalizing this one, and that has happened for all the distributions. I mean there is nothing special about this one, and in this particular case also we can have a multivariate generalization in different aspects, but in this particular one, which has been explored, okay, and many things can be developed. So as you can see that, well, many of the properties of the power normal distribution are very similar to the Azarini's skew normal distribution. Okay. Now let's come to the data analysis part. Again, as I mentioned, that whenever we'll be talking about the data analysis one, so the natural thing is that we'd like to bring the location and the scale parameter, and that's what we had brought it here. So that means that we just, instead of x, we just replace by x minus mu by sigma. So mu become the location parameter and sigma becomes the scale parameter. So now the density function, which can be obtained as simply the way it has been written here. Okay, so everything is then replaced by x minus mu by sigma, and then the associated the Jacobian transformation becomes equal to 1 by sigma. Okay, so that's what it is. So now in this particular case, suppose we try to obtain the maximum likelihood estimator. So again, the standard procedure. So what we can obtain, that we can write down again the joint likelihood, and it's a three-dimensional optimization problem, and so you have to maximize and you have to obtain the maximum likelihood estimator by the standard procedures. Okay, but some of the positive points compared to the Azarini's skew normal distribution, because it's a regular family, it satisfies all the properties of the standard properties of the existence and the uniqueness of the MLEs, and the MLEs always exist. And not only that, the nice part is that the Fisher information matrix is always non-singular. Okay, and therefore the kind of problem what we had faced in case of the Azarini's skew normal distribution function, we do not have that issue because for all parameter values, it is possible to construct the confidence interval of the unknown parameters without much of a problem. Okay, so that thing it can be developed. It can be developed along in the usual process. Okay, so again, what we can see that here, what we have obtained in this particular case, that well, we had this power normal distribution. So if you're looking at our goals, we had put three goals. One thing is that we want a general class of distribution which is not symmetric, and the normal distribution should be a special case, which of course this power normal distribution is satisfying. We want the second one, that we want a heavy-tailed one, which unfortunately even the power normal distribution also does not satisfy. Okay, that is there. Of course, the power normal distribution can be a skewed one. That is the one that was one of our goal. And the third one, that we want to have a multimodality also, but in this case also the multimodality also cannot be obtained, because the power normal distribution is always unimodal, just like the Azarini's skew normal distribution. Okay, So now let me introduce about this the geometric skew normal distribution, which is nothing but a compounding of the new normal distribution based on the geometric distribution. And the way we are looking at it here, we are looking at a geometric random variable with the following probability mass function, where my p is lying between 0 and 1, because we know that the geometric distribution, we can define it in the two ways. One is the total number of tosses unless you get a success, or the number of failures before I get a success. So here basically what we are looking at is total number of tosses required to get a tail, okay, or to get a head, whatever. So that basically that it takes the value from k is equal to 1, 2, 3, 4 like this. So it takes the positive integer value, okay. So probability that n is equal to k is p1 minus p to the power k minus 1. So that's the way we are taking this geometric random variable with the parameter p, okay. So the way we are defining it, it is simply the random sum of the standard normal random variable, or random variable with the normal random variables with mean mu and variance sigma square. So basically, what we are looking at it here, that suppose x1, x2 is a sequence of independent, identically distributed normal random variables with mean mu and variance sigma square, and we are looking at a new random variable x, which is nothing but summation xi, I is equal to 1 to capital N. So this capital N, which is independent, which is a geometric random variable, okay. So this capital N is independent of the xi. That is important, okay. So yeah, so these are independent ones. So what you can see that x is a random sum of independent, identically distributed of random normal random variables. That's what it is, and we call this x as a geometric skew normal distribution. So as you can see that it has three parameters: mu and sigma, which is coming from the normal distribution, and p, which is coming from the geometric distribution. So geometric skew normal with mu, sigma, and p. Okay, so that's what it is. Okay, so now let's see. I mean, as we can easily see, if we just go back here, if you take p is equal to 1, okay, so that means that the extreme case. So n is a geometric random variable with p is equal to 1, which basically means that probability n is equal to 1 is equal to 1. Okay, so since p is equal to 1, so your clearly your n is equal to probability n is equal to 1 is equal to 1. So what happens that in that case your x becomes equal to x1. Okay, so which is again nothing but the normal random variable with mean mu and variance sigma square. So what you can see it here, that well, the normal distribution again is a special case, of course, which is in the boundary of one of the parameter space when p is between 0 and 1. So it's in the boundary, but well, but that is a special case of the class. Okay, so as you can see, that the geometric skew normal distribution, if we take p is equal to 1, so geometric skew normal mu sigma 1 is a normal distribution with the parameter mu and variance sigma. Okay, so now let's look at the cumulative distribution function of x and n. Okay, because that is important, because we need to know the distribution function and the standard method, the way we do that the probability capital X less than or equal to x and capital N less than or equal to small n, which is simply nothing but probability x less than or equal to x, and we are taking n is equal to k is taking the value 1 to small. Okay, the standard way we can make the conditioning that the probability that capital X less than or equal to x, conditioning that your n is equal to k times probability n is equal to k. Now, if you look at it, your x, if you go back to your construction, that x is equal to summation xi, I is equal to 1 to n. Now we are conditioning that n is equal to k. So x becomes equal to the sum of k independent, identically distributed normal random variables with mean mu and variance sigma square. So x turns out to be x conditioning n is equal to k, simply turns out to be a normal random variable with k mu and k square sigma square. Okay, and that's what that is precisely what is going to happen. So k sigma square, and so that is probability that x less than or equal to x given n is equal to k, which is capital Phi of x minus k mu divided by sigma squared. Okay, so that's what this probability that capital X less than or equal to x given n is equal to k gives you. Okay, so that is the distribution function which is coming from the conditioning, and then probability n is equal to k is simply nothing but p times 1 minus p to the power k minus 1. That comes from the geometry. And therefore, if you want the cumulative distribution function of x, of course, you take the your n goes to infinity, and that's what it is happened. The probability x less than or equal to x, which is simply nothing but fx, that probability x less than or equal to x, and then it's finite, so which you have a summation here, which goes from k is equal to 1 to infinity. Okay, because if you put n is equal to infinity, you get the so probability capital X less than or equal to x, which is simply nothing but an infinite mixture of normal density function, and the mixture proportion is a geometric proportion. Okay, and the PDF of x, which simply you can get it by simply differentiation. So again, you can see this one that it's an infinite mixture of the normal density function, and the mixing proportion here turns out to be the geometric mixing. So that turns out to be the density function of this one. Okay, so now let's look at a couple of the simple properties. What it can be, what it has been seen. That again, as I has already mentioned, that the normal distribution can be obtained as a special case. Okay, normal distribution can be obtained as a special case. I mean, as you have said, that it's on the boundary of the parameter space. When you put p is equal to 1, then the normal distribution becomes, you can obtain the normal distribution there. Okay. Again, what we will see that it can be both positively and negatively skewed. And what we will see that, well, it will depend actually on the value of mu. Okay, it will depend on the value of mu, the location parameter. Okay, the positively and the negatively skewness. Okay, because one thing is very, very clear, that if you take your mu is equal to 0, okay, so let's go back and let's look at this particular distribution function or the density function. If you take mu is equal to 0, so your f of x simply turns out to be, small f of x simply turns out to be the p times the mixture of the normal density function with mean 0, which means a symmetric one. And now we are looking at the mixture of a symmetric distribution. So again, that is the symmetric one. So therefore, mu is equal to 0 and gives a symmetric one. And for mu not equal to mu positive or negative, it will give you the positively skewed or the negatively skewed one. Okay, it can have heavy tails, it can have a thicker than that, and it can be multimodal also. And that's what we'll be seeing it here. As we can see it here, it is a positively skewed. Okay, it is a positively skewed one. Similarly, what we can see that it is a negatively skewed here. So, okay, so it can be positively skewed or the negatively skewed depending on the value of mu. It can be multimodal. Again, this multimodality actually depend on many things. It depends on the value of p. It will depend on the value of mu also. Okay, so it depends on the multimodality. Will depend on that, and it can be heavy tail also. That's what it's a thing. Okay. Okay. So now let's look at some of the properties, and one of the standard thing we'd like to see this one, that how does it work if you try to look at the moment generating function or the characteristics function. Okay, and of course the characteristics function always exists, and the moment generating function exists on a particular range of t, and that will depend on the parameter value. So That's what I had put it here. The set A1 is this one. Okay, so then for T belongs to that, the moment generating function exists. But the interesting part is that the moment generating function is in a nice closed form. That is an important part. I mean, it is in a closed form. And of course, whenever we have this moment generating function in a closed form like this, many things can be developed. First of all, the moments and all these things are the trivial consequences from here, but it can be used. I mean, it can be obtained. I mean, lots of these characterizations also can be developed based on the moment generating function. Okay, that is a standard procedure because it is an unique representation. So that's the way you can obtain the many characterizations of this one. Okay, so this the mean, variance, and this gamma, this skewness, all these things are putting it here, and it is very, very clear that, well, as your p goes to 0, your mean is exploding, variance is exploding, and things like that. So all these things it can be seen here. Okay, from these explicit expressions, you can easily look at all these things. Okay, this is another nice stochastic representation of the skew normal distribution. I mean, you can look at the stochastic representation of the geometric skew normal distribution. And suppose I have my x, I should be able to write it, which is in distribution, which is n times mu plus square root of n times sigma z. Okay, where n and z are independently distributed. N is a geometric with parameter p, and z is normal 0, 1. Okay. Again, this particular representation also, I mean, if you remember that we have a similar representation actually in the case of the skew normal distribution also. Azarelli's skew normal distribution also has a similar representation, and that actually helps in many respects, developing many properties. The generation of the samples, all these things can be used. This particular representation can be used, and in this particular case also, many things can be explored based on this representation. Okay, and as I said, it can be used for the generation process. Okay, so for example, that suppose I want to generate a skew normal geometric skew normal distribution. I can simply generate a standard normal, and I can simply generate a geometric one, and I can use this representation, which can obtain that. Okay, it can be used for deriving many properties, as I had mentioned, and not only that, this can be used for the generalization purposes. And the reason that when I'm talking about the generalization purposes, I mean, as you can see that I can change my n. Okay, because in this particular case, I have taken my n to be a geometric one, but I can now, based on these things, I mean, I can change it to any other non-negative, rather any other distribution with the positive support on the positive integers. Okay, or I can even change the z. Okay, instead of the normal 0, 1. So as you can see, I can generalize the process. Actually, I can generalize the process, and most of the properties, because if I know the properties of the z, the properties of the x can be obtained by condition. Okay, so that is also another good part about this the stochastic representation. Okay, this is another important properties of this particular one. It is infinitely divisible. It's a nice theoretical properties, and it is geometric stable. Okay, in the sense that, well, if I take a sequence of independent, identically distributed geometric skew normal distribution, and I take again a geometric. If I take another geometric random variable, say m, and I am taking m of those, then again it is under that. Again, it will be geometric skew normal distribution if I are looking at the sum. Okay, so these are the nice theoretical properties of the geometric skew normal distribution. Of course, we can go ahead and do the all the estimation procedures. Of course, the maximal angle estimators and all these things. We can develop a very convenient expectations maximizations algorithm in this particular case because we have to solve three parameters. We have to solve three parameters. I'm skipping that one now because I'll be discussing those things whenever I'll be coming for this multivariate generalizations because we'll be talking about in a more general term for the multivariate generalization. So we will be talking about the maximum likelihood estimators in case of the multivariate generalization. So you can see this one that similar thing can be applied for the univariate case, of course. Okay, so let's come back to the multivariate generalization. So I have this a bivariate normal, a bivariate multivariate normal distribution with mean mu and the dispersion matrix sigma, and I put it in this form. Okay, that's the standard form, and well. I do exactly the same thing. I mean, I'm looking at a geometric random variable capital N with parameter T, and of course, my capital N is independent of the xi's, whether xi's are the independent identically distributed, and I'm looking at the geometric sum. X is equal to summation xi, I is equal to 1 to capital N. Okay, so again, it is exactly the same way. Whatever we have done in a case of the univariate case, we can do the same thing in the multivariate case. Okay, so let's look at some of the surface plot of this joint, the probability density function, because as you can see, we can develop we can obtain the joint probability density function of the multivariate distribution exactly the same way. Whatever it has been done in case of the univariate case. Again, it turns out to be a geometric mixture of the multivariate density function. Okay, the density function turns out to be a geometric mixture of the multivariate density function. Okay, so let's look at a couple of pictures for this joint probability density function of this bivariate geometric skew normal distribution. As you can see, that the previous one, it shows that it is an unimodal one, but this one shows that it's a multimodal one. Okay, which is possible. That means the multimodality is possible in this particular case, and yeah, lots of this. It can be habitable also. That also is shown. Well. Of course, in the multivariate case also, we have a similar the stochastic representation. So I should be able to write it as x if it is a multivariate generalized skew normal with mu sigma. Sorry, this one should be d. This is not p. Okay, so mgsn d. Okay, so that is a mu sigma p, where x is in distribution, the same thing as before, n mu. Plus square root of n sigma to the power half, and z, where z is a bivariate, sorry, not a bivariate, bivariate multivariate normal, the standard normal with mean 0, mean vector 0, and the dispersion matrix I, and n is a geometric. Okay, so exactly the similar the stochastic representations I have of this n and of this x, the bivariate normal, bivariate geometric skew normal. Here n and z clearly are independently distributed. Okay, so same thing as before. Again, as I said, that it becomes a very simple because of this stochastic representation. It becomes a fairly simple to generate samples from this multivariate geometric skew normal distribution. The standard way, you generate n, which is a geometric p, okay, and then you generate x, which is a divariate normal with mean vector n times mu, okay, and the dispersion matrix vector g. That's it. Okay. So but that's a way. Or as it is, which is equivalent in saying you generate a standard normal, normal from a divariate standard normal, and then you basically use this representation n mu plus this, the same thing, equivalent. Okay. In this particular case also, in the multivariate case also, we can have this the multivariate the moment generating function is in a explicit form. I mean, which is a very nice convenient form where on this set, and of course, if you're looking at the corresponding characteristics function which always exists, and as I said, that this particular moment generating function, of course, helps us to derive the different moments and then the different characterizations and all these things. Okay. Some of the, I think some of the interesting and equivalent properties what we have seen in case of the multivariate normal, we can have this one, that suppose I decompose x as x1, x2, the standard way, and say x1 is say d1 dimensions, x2 is d minus d1 dimension, and similarly I decompose my mu, the vector mu, which is of d1 dimension, mu1, and my mu2 is d minus d1 dimensions, and similarly I decompose my the dispersion matrix sigma as sigma 1 sigma 1 sigma 2 sigma 2 Here sigma 1 is a d1 cross d1, and then rest of the things are so that they're compatible. And if you do this one, that what it can be shown that the x is a multivariate geometric skew normal, and that automatically implies that the x1 is a multivariate geometric skew normal d1 with parameters p, mu, and sigma. Okay. We have a nice characterization also. That means that x is exactly similar to the multivariate normal. That x is a multivariate geometric skew normal with parameter p, mu, sigma, if and only if for c not equal to 0, c transpose x is an univariate geometric skew normal with some parameter mu c, sigma c, and p. Okay, so it is again all these things actually can be obtained based on the moment generating function or the characteristics function very easily actually. So those things that becomes a very useful one, that the characteristics function turns out to be very useful for that purpose. Okay, and it is exactly the similar characterizations what we had in case of the multivariate normal. Okay, so that the linear combination is univariate if and only if the whole vector is a multivariate geometric skew. Okay, we have another characterizations which is which basically gives it that, well, it's a kind of a geometric stability which brings it. Suppose x1, x2 is a sequence. That's what I said. That one that it's a geometric stable, and that's what the characterization also gives us. Suppose x1, x2 is a sequence of IID d-dimensional random vectors, where m is a geometric alpha. M is a geometric alpha random variable. Okay, and so suppose m is a geometric alpha random variable and m is independent. Okay, m is independent, and suppose my y is equal to summation xi, I is equal to 1 up to n, and then y is a multivariate geometric skew normal if and only if my each of the xi's is a multivariate geometric skew normal. So this is again one of the characterizations what we have for the multivariate geometric skew normal. There is another nice decompositions which has its own importance. I mean, suppose Q is a Poisson random variable with parameter lambda, and Z1, Z2 is a sequence of IID random variables with the following probability mass functions. And suppose all the random variables are independently distributed in the sense that the Q zi's, they are all independently distributed, then X has this following decompositions. Okay, X is equal to Y plus summation Y and I is equal to 1 to 3. Okay, so this one is a nice decomposition what we have. Okay, so now let me come to the point that when we are trying to define, when we are trying to discuss about the maximum likelihood estimations, we are trying to looking at the estimation procedure of this geometric skew normal distribution. Okay, so now let's look at how many parameters we have. P, we have one parameter. In mu, we have d parameters, and in sigma, we have d into d plus 1 by 2 parameters. Okay, so we are trying to obtain the maximum likelihood estimations of the unknown parameters. And suppose my d, that's a sample I have. Each one of them is a d-variate sample I have. So I have n of those. So you can see that even if my d is equal to 5, even if it's a 5-dimensional one, I have almost 21 parameters. So clearly, it's a difficult task. I mean, it's a difficult task to optimize, to find out the maximum likelihood estimators if we try to do in a brute force manner. Okay, because as we know that it's a multi-dimensional optimizations, we need a very good starting values. I mean, we have issues about the local convergence. All these things are there. Okay, even we have issues about even the convergence also. Okay, so yeah, so this is my the likelihood function. If you're looking at the log likelihood function, as you can see, I mean, and it is the density function. It is in the infinite summation. Okay, so that makes it slightly complicated. Okay, as you can see that, I mean, it is not a very easy thing to optimize. So of course, for that reason, I mean, we'll fall back on our favorite expectations maximization algorithm, which really helps in this particular case, and really, actually, that will be very useful in deriving the maximum likelihood estimators in this case. Okay. So therefore, to compute the MLEs, we need to maximize with respect to the unknown parameters, unless the multivariate normal, when my p is equal to 1, the MLEs do not exist in the explicit form. Okay, so therefore clearly the maximization is not a trivial problem, even if d is not very large. And whenever I'm not talking about the very large, I mean, even as I can see, even with the 5, 6, we have a more than 20-dimensional optimization problem. So. So what we do, we use the profile likelihood method, okay, and that we combine with the expectations maximizations algorithm, okay. So the way we proceed, that we assume that suppose my p is known, okay. Suppose my p is known, and so we treat this problem as a missing value problem, a standard way. So what are the missing values? Well, the missing values are simply nothing but as if we have the complete observations of the form x and the associated the geometric one x and n. Okay, so suppose we have these are the complete observations I have. So actually, what we are observing, which is my x, but suppose we had observed n also. So suppose the complete observations is of the form of xi mi for I is equal to 1 to 3. So this is my complete observation. So suppose I had this complete observation. So now let's look at what will be the maximum likelihood estimator. Okay. So let's write down the log likelihood function of the complete observation. Okay. So which simply turns out to be, because now you can see that each of the xi's which are coming from a multivariate normal with mean mi mu and dispersion matrix MIC. That's what is going to happen. Okay, and that is precisely what we had put it here. Okay, so what we are written the complete log likelihood function, which is in this form, and now this becomes a quite trivial problem in the sense that suppose we denote my k is equal to summation mi, which turns out to be, which gives me basically the maximum likelihood estimator of mu, which simply turns out to be 1 by k summation xi, which is in a explicit form. And the same thing with the dispersion matrix also, the sigma c hat, which is the dispersion matrix, which is 1 by n, and in this form. And the dispersion matrix sigma c hat, which can be easily obtained by differentiating the log likelihood function. The standard way, the way we obtain the dispersion matrix of sigma in case of the standard normal, exactly the same procedure we follow, and we obtain the dispersion matrix of sigma hat c for the complete data set, which is in the explicit form. And that is precisely the idea about that is precisely the reason behind the EM algorithm, the idea behind the EM algorithm, what we'll be following. Okay, so we'll be using this particular case. So whenever my mi is missing, because mi's are coming from n, so what we do, we basically, I just want to replace this mi by the expected value of n. Okay, expected value of n given the observation x is equal to x and the corresponding mu and the sigma value. So this expected value of n given x is equal to x mu and sigma, which can be obtained in the explicit form. Okay, and therefore we'll be using that one. So wherever my mi's are there, I'll be just replacing by the expected value of n given x is equal to x. And again, the way for a given p, we obtain the estimates of all the quantities, and the standard way when we try to obtain the profile likelihood method, we then estimate p by using maximizing the profile log likelihood. Okay, so that is the procedure what we can follow, and that's what it is. So the process continues till the convergence takes place. Okay, so that's the way it goes. Okay, so as we can see, the interesting part is that, I mean, as we can see it here, so because this the mu and the sigma are in the explicit form, therefore my E state, of course, it involves some computation because I need to compute this expected value of n at each of the E steps. I need to compute this one, but these expectations are basically summations. Okay, so those summations we can do it very quickly. So expectation of n. So each step, it takes some time in the sense that, well, I need to do all these expected values. But when it comes to the m step, I don't have to solve any problem. I don't have to solve an optimization problem because I have the explicit solutions. So you can see that, I mean, it really actually helps because, I mean, as I mentioned at the beginning itself, even if with your d is equal to 5, there are 21 parameters. Okay, so you can see this one, that if you increase your d, if you put d is equal to say 10, you can see that 1 plus 10, 11 plus 5 into 11, 55. So you can see that how many parameters you have, more than 60 parameters you have. So 60 dimensional optimization problem. But in this particular case, actually, the nice part about this one is that, of course, the computation increases with d, but not that exponentially. Okay, of course, the computation increases because of this calculation, expectation of n calculation. Because that expectation of n calculation, of course, it becomes a more and more as my d increases. Okay, but still, it is not that much rather than your optimization problem. Okay, so anyway, so that's the way this EM performs, and what we have seen that extensive simulation has been seen, and the proposed EM is quite fast, and it is scalable, as I said. For the high value of d. So it does not increase that much. Of course it increases. I'm not saying that it does not increase the computational time, but it does not increase that much. And not only that, we usually do not have any problem about the local optimum and all these things. Okay, so that is one of the nice part about this particular case. Okay, So now let's look at some of the related models, and I think what is important. Okay, so one of the model what you can think of, what you have seen that that suppose you're looking at the regression model. Okay, suppose you are looking at the regression model, what we call this one as a geometric skew normal regression, and suppose your epsilon I is a symmetric one, but it has this the geometric value p. So that means that it can be multimodal, it can be Hermitian. Okay, so suppose it is your yi, which is xi transpose beta plus epsilon I, and again, as you can see that our standard assumption is that when you take this regression model, that the errors are independent, identically distributed, normally mean zero and variance sigma squared. So again, that can be tested also based on the data. Okay, so suppose your errors are multimodal, or the errors are maybe heavy-tailed. So the geometric skew normal distribution, symmetric geometric skew normal distribution can be taken as the error random variables. Okay, and in this case also the maximum value estimators of the unknown parameters can be obtained based on the EM algorithm. Okay, so that is definitely one of the things which has been which is a nice thing. Okay, another one. Suppose you are looking at the geometric skew normal distribution because it is on the entire real line minus infinity to infinity, and exactly the same thing what it has been done in case of the log normal. From the normal distribution it go to the log normal one by simply taking the exponentiation. Okay, and suppose we do the same thing over here also. Suppose we are looking at a new random variable, say y, which is y is equal to e to the power x. Okay, suppose we are looking at the exponentiation of the geometric skew normal distribution. So then y becomes a lifetime distribution. Okay, y becomes a lifetime distribution, and suppose we go ahead and look at the log GSN distribution, just like the log normal distribution, and yeah, many things can be developed. Okay, and definitely we can develop the testing of hypothesis in general for the geometric skew normal distribution, or for developing the Bayesian inference. The classical inference which has been done and which is working fine. But suppose we are going for a Bayesian inference also. Those are the things which can be used. Okay, I think I'll stop it here. These are some of the references along that line, and I think I'll stop and I'll keep it from the questions. Okay, thank you.
Thank you, Professor. Thank you so much. In fact, now audience, anyone can. Someone has raised the hand. Whether Signa, whether she. Kalyanam, sir.
Thank you very much for your nice presentation, sir. Learned a lot of things. And generally, normal distribution, we are all very old people. So, normal distribution, symmetry and asymmetry, how it goes with that. Is it not necessary that you find a separate name for that?
What is that? What is
this? Normal distribution means we are told in the class, the first class itself, it's a symmetric distribution and all that. And when you say asymmetric normal distribution, naturally it gives kind of a confusion. So, is it not necessary that a new name to be coined for that?
See, this skew normal becomes a very, very popular one, and which is turns out to be as a where the normal is a special case. So, that's the reason that we are giving the name as a geometric skew normal. Yeah. So, well, yeah.
A lot of information was provided, and I think it may take some more time for people to come out with their own ideas about it. Thank you very much for that.
Thank you.
Hello, sir.
Hello.
Yeah, please.
So actually, session was amazing. Sir, I have a question. Just suppose you have a data and we don't know, initially we don't know the distribution. Then how we will decide that which distribution you should take? Just like skew distribution, just like we have a survival data, here tile always positive, then how we will decide we have to take log normal, log logistic, or in any one of the skew normal distribution or power or geometric normal distribution?
Unique way. I mean, so that's the reason that we have all these different goodness of fit tests. I mean, that's the thing I will suggest. Okay, so we will go with the goodness of fit, and whichever gives you the best one, you pick it up from there. So there is no unique way of defining. But see, the thing is that whenever you try to fit a distribution to a given data set, if you have some background of the data, which is always useful because you know that from which process it is coming, and so if you can associate that with any physical process, and many distribution has their own physical representation also, interpretation also. So if you know this one, that is always useful. But if you just try to use as a data fitting, then I would say this one that, well, you try with the different models and you go for the goodness of fit. I mean, that's the way it should work. Okay. Well, Bala is sitting there. Bala can give a much better comments on that because he's but this is Bala, please. This is a general.
No, you have already explained. I think generally the technique, like you explained, you have a basket of models.
Yeah.
You want to fit all of them and see using some goodness of fit, some model validation techniques, which model is a good working model. That's the only way. By looking at the data, you cannot guess because many unimodal distributions look alike. So the only way to do is to use some model validation techniques.
Okay, sir. It means that we will check one by one, and then by model validation, we will find the best one.
Yeah, that's what it is. A basket of one. I mean, you have maybe a 5 or 6 or things like that, and you see this one that how does this model validation, the goodness of it works. Okay.
Okay, sir. Okay, thank you so much, sir.
There are two people.
Sir, good
who have
morning.
raised their hands.
Yes, please go ahead. Yeah.
Satish, there are two people who have raised their hands.
Yeah.
Yeah, sir. Sir, good morning.
Yeah.
I
Good
have
morning,
a
good
small
morning.
doubt.
Yes.
Sir, when now we are having so many parameters involved in the new kind of distributions. So out of those parameters, how can we identify, what is the importance of location and scale parameters? Is it necessary for every distribution will have a location and scale parameter? Or among those parameters, how can we identify which parameter is location and which parameter is scale, etc.? Can you brief?
No, location and the scale parameter has a very, very specific definition. Okay, so whenever you are talking about the location one, say suppose I call this one as a mu as a location parameter. If x minus mu, okay, if x minus mu is independent of mu. Okay, if your distribution of the x minus mu, suppose x has a location parameter mu, so the distribution function of x minus mu will be independent of mu. I mean, that will be calling as a location parameter. Same thing, we have the definition of the scale parameter also, because we know that suppose mu is the location and the lambda is the scale, so which basically means that the x minus mu by lambda is independent of the mu and lambda. Okay, so these are these are the definition what we have for the location and the scale. So now, whether each distribution should have the location and scale, well, not necessarily. I mean, that I think, see, it will just gives you the more flexibility of the model fitting. But then at the end of the day, I mean, you can again go for testing whether the mu is at all present or not. You can go for the testing from the data, or your lambda is necessarily present on the node. I mean, you can easily go for the testing for the data. Say, for example, testing of hypothesis, say lambda is equal to 1, and that will basically tells you that, well, you do not have a scale parameter in the data. Okay, so it is just gives you a more flexibility. I mean, you have a more choice, but then at the end of the day, you can go for testing, and then you can discard also if you find that those things are not necessary. Okay.
Okay, sir. Thank you. Thank you, sir.
Sure.
Okay, I think Signa has wrongly raised the hand. So, anyone else, please? Any other questions? So, if there is no questions, let us conclude this session, because now people can contact Professor Kundu via online, if via email or any other means, if
Sure.
they need.
Yeah.
And all other, anyway, let us have a very wonderful talks by Professor Kusubovsky as well as Professor Kundu on behalf of the Department of Statistics, University of Kerala, and the School of Physical and Mathematical Sciences, University of Kerala. We would like to extend our gratitude to you, professors, Professor Kusubovsky and Professor Kundu, for your very excellent talks, and they are no doubt they will be useful to the youngsters. Also, the presence of Professor Bala also raised the and motivate the youngsters to think about different way of approaches. On behalf, once again, thanking you. There are several professors from all over the world in this group, and also apart from more than 80 are there, always there in this group watching this talks. In fact, the several are there in the YouTube Streamline channel, and several are benefited. Tomorrow we have in the lectures in this workshop on the evening time from 5 p.m. onwards, Indian time, IST, 5 p.m. onwards. We would like to invite each one of you to that talks also, and we are grateful to each one of you for your support and blessings. And once again, thanking you, professors, Professor Kalyanan sir, Professor Balakrishnan sir, Professor Kundu sir, and I think other professors. Thank you so much. Thank you. Yeah.
Bye, Debashish. Bye.
Bye, Bala.
Good night.
Good night.
Okay, bye.